From our daily experiences, it looks like the whole universe is ruled by Newtonian laws. But they start showing some limitation when we deal with waves and fields.
Ah, gravity, thou art a heartless bitch.
Indeed, the three laws are for local mechanical interactions. Introducing fields in our universe, observations and results contradict Newtonian rules. And even gravity that follows Newtonian gravitation is actually not Newtonian.
And you may want to put on a seatbelt.
We state gravity is not a force. But then we treat it as it is. We compare it to Coulomb when we use Newton with gravity. And free fall on Earth is considered acceleration. We assume force following the second law. Gravity is the acceleration and the interaction is made Newtonian. So here we see the force of gravity at large and smaller scale. When instead we treat gravity with Einstein, we talk about space-time curvature without direct force on masses. At first approximation, both models work, despite the apparent contradiction in the fundament. So what's the point about forcing gravity if in practice this concept doesn't seem to make any difference? A force is related to measurable accelerations against conservation of momentum. When there are no local accelerations, no force is acting against the motion of the system. Gravitational interactions violate all three laws, because masses move to conserve momentum. Free fall is a good way to see why gravity is not a force. There is increasing speed relative to the ground, but despite we are moving faster and faster, we can't measure accelerations. Without external references, this condition is no different from floating in an empty universe. Only the local values matter, and we are weightless. So it is wrong to have this force for gravity. It would be better to call this a gravitational interaction since it's a potential difference. It wouldn't change that the gravitational field of a big mass can affect the way surrounding objects are conserving momentum without accelerations. So when we free fall, we are not moving because of a force, and velocity here is making no difference to the free faller. Right now, Felix is one of many other equivalent frames of reference, as floating into space or aboard the ISS, meaning all of them will give identical results in any experiment we perform. So even if the observer on the ground sees an increasing velocity, gravitational interaction is causing downward movements with no acceleration in violation of the second law, but showing why is not a force. On Earth we have the other side of the equivalence between frames. Experiments and observation here are identical to those into a rocket accelerating at 1g. These results are anyway different from what we get with inertial frames, since touching the floor, Newtonian laws act with forces and makes everybody accelerating, observer included. It inevitably follows that there is no third law within gravitational interactions. Without force in first place, there can be reactive force. Meanwhile, on the ground, Newtonian interactions are occurring as usual. Gravity is Newtonially weird. It affects how you conserve momentum. Two masses attract when big and close enough. It looks like this is the symmetry of the third law. But with Newton, the forces act as contrast. The symmetry comes from two systems that don't want to move. If I pull, the object wants to stay away. If I push, it wants to stay close. That's the whole point of force-acceleration relations. On the other hand, motion because of gravity comes from mutual agreement, This is another important distinction from Newtonian laws. The two are willingly getting closer. You don't need force. In gravitational interactions, we lack the inertia opposing to motion. Gravity affects the least action of conservation of momentum. Thus, here, mostly because of Earth, each system wants to conserve some momentum toward the other. Magnitude is defined by masses and distance, and gravity too relates to conservation of momentum. So it looks Newtonian, but there is no acceleration. And obviously, momentum is symmetric, but the huge difference in inertia makes, in practice, only Felix moving toward the planet. It's freefall. Combining everything said until now, we see that because of gravity, we want to conserve momentum toward the Earth. The observer on the ground is thus exerting force against the floor, trying to keep its state of motion. And the ground reacts with the opposite force. This is the force we feel. And it's the combination of these two that give us weight. Freefall has no weight. It can maybe still be weird to think that who's conserving momentum is the one we observe falling. Felix is definitely increasing velocity, so how this is not acceleration? We already distinguished two states for each system according to the measurable acceleration. These conditions represent the most evident difference between inertial and non-inertial frame of reference. On one side we have equivalence between all inertial frames.
And then we're going to see what will happen when we ring it out. Meredith and Kendra
And likewise, all non-inertial frames are equivalent, whatever the source for the measurable acceleration.
In real life and in physics, I will tell you that the force on this ball...
The acceleration found in these frames will affect experimental results and observation with respect to inertial frames. And even more, when non-inertial frames have different accelerations, experimental results and observation will disagree even between them. So it's not about how it looks like. The type of frame is defined by what is locally measured. If I accelerate while observing a system with inertial movement, it is possible to see a curved trajectory for something that the inertial observer sees as a linear conservation of momentum. From the rocket we can tell the curvature is apparent, since this distortion exactly matches the local measured acceleration. The ball is not following a curved path, it's this accelerating frame of reference that is affecting the observation. While between inertial frames, relativity allows each observer to consider itself still, acceleration is absolute. It's true for the entire universe. There is no question about the subject, and it's no opinion the amount. So the one measuring acceleration must account for the local magnitude to understand observation from its frame of reference. And it also means that you cannot consider yourself stationary while you are measuring accelerations. So everything we do on Earth use as reference a frame that is undoubtedly accelerating. It's weird, but we are used to. There are constantly alternating inertial and non-inertial states, and accelerated systems may appear to stand still. But here, the only absolute motion lies in the observer on the ground. So the freefaller is not accelerating, and until now we held on this solid point. If you measure acceleration, you are not conserving momentum, so for at least this part of motion there is no doubt, regardless of the relativity. But because of gravity we have momentum toward the Earth, and we need to apply force if we want to stay at a constant distance. This is the same frame of reference we use on Earth. We consider ourselves stationary because we assume stationary as constant distance from the center, but it's our convention since we are not at rest, and we are using a set of constantly accelerating coordinates. In this fashion, even the astronaut inside a rocket could consider itself stationary. This assumption is just as arbitrary, because magnitude won't change that they are both non-inertial. It's maybe counterintuitive that you don't go anywhere even though you are constantly accelerating, but the effects of negative and positive acceleration are indistinguishable. Without external references, we can't tell if what we are measuring is acceleration or deceleration. Seeing how gravitational interaction works, seems now pretty obvious that we on Earth are constantly decelerating. The ground expresses force that counteracts the momentum we want to conserve toward the planet. From Earth, systems are approaching at increasing speed, but it's yourself around the ground constantly decelerating. We can also pinpoint that a free-falling charge is not accelerating. The charge on the table is, and this is no opinion. It follows that asking, does a charge radiate with every measurable acceleration? We just have to look around. Everything is accelerating. No particle seems to radiate because of this. Gravitational interactions agree with first Newtonian law if we consider conservation of momentum as lack of measurable acceleration, but disagree about spontaneous motion with changing velocity. As a system conserves any kind of speed, including no one, so much it shouldn't spontaneously gain momentum, but stand whatever it is. Yet it moves. Gravitational interaction is not just contradicting the first law, but all Newtonian mechanics. While it's conserving motion, it can change velocity to masses with no use of force. Indeed, this is the problem in trying to combine gravity and force. You need exceptions and special cases, since gravitational dynamics don't agree with the three Newtonian laws. Felix is moving with some momentum when it's close enough to the Earth for the gravitational interaction to be noticeable. The two bodies are now conserving a very specific amount of momentum in a very specific direction. The motion is still relative. We don't measure accelerations, but the magnitude is not questionable. It's no opinion how much momentum he has because of Earth's gravity. Our condition now speaks of some generic velocity with typical relative meaning and this sort of absolute relative motion. Even here velocity is relative, but no observer can change the objective quantity for this gravitational interaction. There is only one true rate of approach for these two systems, with no care for the apparent. This velocity becomes now highly questionable, meaning there are definitely preferred inertial frames in which the interaction occurs and makes sense with finite specific velocities. I can say Felix is moving at thousands of kilometers per hour with respect to the galactic center, but this velocity won't explain why he will fall on Earth. So here I can't use any arbitrary velocity, as this momentum 2 is now better defined inside the interaction and have absolute values from this preferable frame. The effect of gravity on conservation of momentum can also be seen this way. From far away, Felix will slowly, inevitably move close to the attractor just to conserve momentum, and he will do it with increasing velocity. But when we give some rotation to the planet, this is the free fall toward the center. Momentum conservation will be a curved trajectory because of the gravitational drag. Now, it may look there is a shorter path, but conservation of momentum refers to the least action of inertia, not what it looks like. With no additional velocity, this is how we conserve momentum, not that way. He has to use energy, force, and accelerate against momentum conservation to follow that line. Now, he maybe think itself on the fastest straight path, but as soon as the force stops, he is back again with momentum conservation and a similar path for the free fall. And actually, this momentum keeps existing the whole time. So the force is additional. Its contribute affects the overall motion of the system and how momentum will be conserved. So here now we must also account for the velocity from acceleration. With gravity we still have the relativity of inertial frames, but since we have an interaction, some velocities are less arbitrary and some frame preferred. In the end, conservation of momentum with gravity results in motion as least action. Gravity has no force is more than a statement, but the force-motion relation is easy because it still involves conservation of energy, so it's not about the wording. This is another good example in showing how gravitational interaction would behave being a force.
Different directions. But there was a preferred direction.
Momentum is gradually dispersed until they all stop at the center of the well.
But one thing you can't do with those.
Gravity doesn't follow the 3 Newtonian laws. They refer to different types of interaction. On Earth, these two continuously mixes. We exploit the combination of inertial and non-inertial frames.
This, Chris, you want to know what was the motivation here? Miles. Absolutely. That's why he walked off with his thumbs down like that. He did not like the fact that the people were a little less than happy.
But all Newtonian mechanics we are used on the planet are missing at orbitational scale. It may therefore be helpful to think at the whole universe as constantly free-falling.